Welcome back to What You Will Learn. My name is Adam Ashton.
And my name is Adam Jones. Today we're taking you through the best bits of A Brief History of Time by Stephen Hawking, from the Big Bang to the black holes.
Stephen Hawking, very well respected bloke in this field. This book, probably one of the foremost authorities on this topic. Over 10 million copies sold, a couple of 100,000 ratings on Goodreads, which is, I guess, the authority we go to determine the popularity of a book. And he covers a wide range of different things here about space, about time, and everything in between.
So Stephen Hawking, he did pass away in 2018, which was a big loss to the world of science. And quite an inspirational man. In 1963, he was contracted with motor neuron disease, was given 2 years to live. And here we are, 57 years later, and he's done two difficult things. He's contributed to science with a lot of academic papers and pushing that forward, but then also popularising a lot of these concepts. So the everyday readers like me and you, Ash Joe, we can actually get a piece of the action. So there's no bigger book in science, I think, in popularising all these concepts than this one, A Brief History of Time. It was actually the first book that I ever read, first non-fiction book. It was given to me by my great uncle when I was about 15 or 16 years old, and since then I've probably read this book 3 or 4 times.
Very interesting. Matt, that's an interesting entry point. Probably not the easiest book to start with, but obviously it didn't turn you off, so that's good.
Well, there's another version that's called A Brief History of Time.
Oh, nice.
And that's what I started on.
That might be my territory. Mate, so in this episode, we're going to cover space and time, we're going to cover black holes, we're going to cover quantum mechanics, and then we're going to cover the origin and the potential fate of the universe. From the time of Aristotle, a couple of hundred years BC, all the way through till really like the 18th, 19th century, science as we know it today was referred to as natural philosophy. That's what Peter Singer told us as well, that it was, philosophizing about nature. And what that meant was like there were people sitting around and thinking and talking and discussing different ideas and different thought patterns, but there was no one actually going out there and doing experiments to test in the real world. They were just thinking, oh yeah, this sort of makes sense, and philosophizing about it. And then Galileo came along and started doing some experiments. So I guess in popular culture, people think he went up the Leaning Tower of Pisa and dropped different balls off to test it. Hawking reckons that's probably not a completely accurate story, but he was doing experiments.
Yeah, it'd be an odd time. You knew if you jumped up, you'd just fall to the ground, but there was no real reason to explain why you just kind of magically just dropped down. There was no science to back it up. One of Galileo's first experiments was he got 2 balls. He had one heavy ball and one light ball, and what he measured was that the heavier ball travels down the slope at the exact same speed as the light ball. And this kind of went against the popular belief at the time.
Yeah, you would think that the heavier one would drop quicker because it's heavier, so it's going to hit the ground.
It's kind of intuitive, isn't it?
Yeah, it makes sense if you're thinking about it.
But no one ever tested it.
Yeah, for sure.
No one really ever tested that out.
So Hawking was saying it's probably too hard to, if you drop 2 balls at the same time and watch them falling through the air, it goes too fast to actually tell the difference in speed. So what Galileo did was he had like this slope where he rolled it down the slope. So it was going slower and you could actually observe it. But what he saw was that they were both going at the exact same speed, which is kind of weird.
So Sir Isaac Newton, he was the one who took Galileo's experiments and took them one step further to make laws of motion. And these 3 laws developed in 1687 are still widely used today. Every structural engineering equation is grounded in Newton's laws of motion. So most of what you need can be found in these 3 simple laws.
Another romanticized story is, Isaac Newton was sitting under a tree thinking and an apple dropped on his head, and that's what sparked his idea of gravity. Hawking says it's probably another romanticized story, much like Galileo dropping metal balls off the Leaning Tower of Pisa. But it's sort of one of those things that this combination of different scientists working together, doing experiments, taking each other's work, questioning the long-held beliefs. Of course, the church, I believe they locked Galileo up for his crazy ideas, thinking that the Earth wasn't the center of the universe and not everything was revolving around the Earth. But it was all these ballsy people who were going out there and testing things out, willing to question the authorities and try to get to the source of what's actually happening out there in the world.
One of the wildest concepts he came up with was the idea of gravity. And in his equation, he showed that gravity is proportional to the mass of the body. So Astro, you got a bit of a gravity around you. If you got someone, you do have a bit of
nice.
you got a higher gravity than me because you're a bigger boy than me.
Is that a metaphorical gravity as in people are drawn to me, or an actual literal
That's
gravity?
probably the worst possible gravity. Means you got a high center of mass. And then if you got a sun, for example, it's got higher mass, so then it's got a bigger gravity and so forth. So it's a function of the mass in the body is the gravity. And then also how far you are from the center of that mass is also proportional to the gravity. So the closer you get to the sun, for example, the stronger the gravity is. So say if you got something like the Earth, the closer you are to the very center of the Earth, the stronger gravity is. But the further you are from the center of the Earth, the weaker it is. So if you're in orbit, for example, it's obviously weaker the further you go outwards. And with that, for every action, there's an equal and opposite reaction. So even though, Astro, you're sitting on the Earth now, you've got your own gravity, Earth's got its own gravity, you're pulling Earth up at the exact same amount that Earth's pulling you down, which is a really kind of odd thing, isn't it?
It certainly is. And so a bridge of these discoveries of these laws of motion, that brings in the ideas of time. So both Newton and going all the way back to Aristotle, they believed in absolute time, as in there's some kind of magical clock and it ticks for 1 second every single second, and everywhere in the universe experiences that same amount of time is in 1 second per second. And it's just this absolute thing that there's the magical universal clock, and that's what time is.
Yeah, there's no real reason to think otherwise. But as Galileo planted the seeds for scientific observation and experiments, Olaus Roemhurch in 1676 first successfully measured the speed of light. So prior to that, light's just everywhere flying around. No one really thought about it. He actually observed that it has a fixed speed. And the most interesting thing about it, it's got the exact same speed in every direction, and no matter how fast the observer is going. So say if you're in a car driving 60 kilometers an hour and a car travels just past you at 70 kilometers an hour, it's really only traveling 10 kilometers an hour relative to the first car. If it was going the opposite direction, it's traveling 130 kilometers an hour in the opposite direction. But when it comes to light, if you're traveling in one direction and light's traveling in the opposite, technically the speed of light should change relative to what the observer is. But what our man Olaus found was it doesn't matter what the observer's doing, the speed of light is a fixed exact number no matter what direction it's going.
So we've got two seemingly contradictory ideas here. We've got Newton's got his 3 laws of motion. They all seem to hold very true. And then you've also got this guy, I forget how you pronounce it. That's the one. And so he found that, okay, well, actually, the speed of light seems to be constant in every single direction. Doesn't matter what you're doing. So you've got two contradictory things here, both mostly true. But then you've got the great man Einstein comes along. He does his wild thought experiments that we spoke about in the Mastery episode, where he's, not trying to solve it. He's almost going back to the Aristotle style of thinking about it. He pictures himself riding on a light beam towards a train. If the train is heading towards him and turns its lights on, how does he see those lights? He's doing all these crazy thought experiments, and he realized, okay, well, if we've got fixed laws of motion, but we've also got the space that the speed of light is fixed, then perhaps the variable here that could explain that time could actually be variable. So rather than Newton and Aristotle thinking that there's an absolute universal time for everybody everywhere, perhaps time is actually not fixed.
So the big point here is time is going to be at different speeds depending on how fast you're traveling with the speed of light. This is Einstein's big papa. So if you're Billy Bean in your year 3542 Ferrari going close to the speed of light, time is going to slow right down. If you take it a bit further, and let's say hypothetically you could travel at the speed of light, you're basically traveling with time. That's impossible to do, but worth mentioning just for the discussion of this. And then if you were to travel faster than the speed of light, you're basically going backwards of time. So time is completely relative to the speed of light that you're actually traveling at. Then if you're our man Joey on a Friday night sitting there drinking beers, watching the TV and eating pizza compared to Billy Bean on the Ferrari, time is going to be going at a completely different amount of time for you. It's going to be much faster relative to the person with the speed of light. So every single person, me and you, Astro, we got holding 2 different own personal time clocks. If you were to go to the moon and back, for example, at a certain speed, you're going in different time zones. But because we're nowhere near the speed of light. They're so close together, we can't really tell the difference. So it's all to do with your acceleration. And remember we mentioned earlier about how gravity is actually acceleration. So the greater the gravity of an object, the greater the acceleration one is feeling. So the closer you get to the center of mass of a big object like the sun or the earth, the stronger gravity is. And the further you are out, the weaker gravity is. So the acceleration you're experiencing weakens the further away you get from the object. And you can see that with rocket ships, for example, trying to leave the Earth. The gravitational pull is much greater the closer you are to the center of the Earth.
So Einstein's theory of special relativity was saying that time can speed up or slow down depending on how fast you're traveling. But his general relativity was saying that gravity can also bend time. And so like you said here, like if you're closer to the center of mass, gravity is actually stronger. And so there's a paradox here called the twins paradox. You've got two identical twins that are born. One of them lives at sea level. One of them lives on the top of a big mountain. So the person who's on the top of the big mountain, much further away from the center of the Earth. So gravity is less strong on that twin compared to the twin who's at sea level. Gravity is a lot stronger because they're closer to the center. So you'd think if time was fixed and gravity didn't have any impact on it, then they should be both aging at the exact same rate because they've got this absolute universal time. So for the twin who's at sea level, because gravity is stronger, that means time is actually moving slower, so they actually age more slowly. Contrast that to the twin who's on the top of the mountain. Gravity is weaker, so time is faster, so they're aging more quickly. So basically, if you want to live longer, get closer to sea level. Is that right?
Well, because you're holding your own clock, so you're not living longer. But for someone who isn't as so-called traveling at this close to this speed of light relative to you, for them it seems like you're living longer. So you're really just basically stirring up envy with the other person, which is maybe a good goal for some situations.
That's so funny. We'll try and bring it to some pop culture stuff as well. The movie Interstellar, Matthew McConaughey, yeah?
Yeah, Matthew McConaughey. I think he plays a guy called Coop, looking to save the world, explore new planets in different solar systems when a wormhole just opens up out of nowhere. And the big risk here is because they're doing interstellar space travel, because they're moving near the speed of light, as Coop, as he goes near and closer to the speed of light, time is going to go much slower for him at this speed compared to all his family and loved ones back on Earth. For them, time's going slower. So there's a real risk that if he doesn't get this done in a certain amount of time, of his own relative time, everything back on Earth is going to be tens and tens of years later, and he's not going to see anyone in his whole entire family.
We've got to be careful. I don't know if this is a spoiler or not. I know people hate spoilers and stuff. So if you haven't seen Interstellar, it's definitely worth a watch. If you haven't seen it, maybe skip forward 60 seconds. But so is this like saying how, because he's going so much faster, when he can come back, he feels like he hasn't aged. Compare that to his family who has aged. I just remember how he's in the back of the bookshelf and his kid's grown up and he's throwing books out.
Yeah, exactly. Well, that's going maybe next level. That's beyond the point of what we're trying to say.
Okay. I don't know if I fully grasp it yet.
Yeah, that's after he falls into the black hole. That gets pretty speculative into the unknown and nothing to do with Stephen Hawking here. Astro. I'll tell you what is, though, when they're going past this planet called Gargantua, which is right near a black hole. Think about the acceleration of a black hole. The mass is so big that gravitational pull is just well beyond anything we can imagine. So any object that is in that gravitational pull of the black hole and this planet Gargantua, they make up the number. Every hour on that planet equals 7 years time on Earth. And that's why, because you're accelerating so fast, closer to the speed of light relatively, time is going much slower for you than the people on Earth. So that's why the huge risk is sitting in there.
Hang on, so I think I'm starting to grasp it. So is that like, because it's a very big planet, very strong gravity, and because you're getting closer, gravity's so strong, you're traveling so quickly, and that means time slows down, yeah?
Correct.
Nice, okay, yeah. I
And
think
for
that,
you,
is that
'cause,
when
yeah, well, it kind of comes back to the Newton's law as well. You're not physically traveling because you're standing on a planet and the planet is pushing you back at the same rate you're pushing back in because of general relativity. It doesn't matter about that. So for you, it doesn't feel like you're not physically just flying around the air at a certain speed. You're still standing still, but technically you are still accelerating due to the gravitational pull that you're experiencing.
I might be mixing different movies here, but there was a planet full of water. They go down there, the ships crash. They want to get off as quickly as they can because they know when they're down there, time doesn't feel like it's moving for them, but back on Earth, everyone is getting older.
Exactly right. And that's why the person, when they get back to the rocket ship, I think for that person in the rocket ship, he was there for like 3 or 4 years just by himself, the poor bloke. And all McConaughey's team down there just for 10 minutes having a ball on an island riding tidal waves.
I think I need to rewatch this movie having read this book now because I'm starting to get it a bit more. I just remember it being a big mind screw at the time.
Stephen Hawking did a lot of work around black holes as well, which he makes really accessible and easy to understand. So back to your scene where McConaughey, I think his name's Coop in the movie, is pushing out books and the sorts because he hopped into a black hole. And what the movie's doing, it's got a bit of a creative license to do whatever the hell they want because we don't know anything about what's going to happen when you go into a black hole. So the general idea is whatever comes into the black hole, it's absolutely infinitely impossible to come back out of it. That's all we know at the moment. It's a point of infinite density where all the mass and matter and everything just collapses into a single point in space. But even that's not really right because it's not really a point in space because it's got zero volume, essentially.
Hawking refers to black holes as a singularity in that it's this one single point where it's got zero volume. And because it's got zero volume, it means it's got infinite density because all that mass inside of that star has been collapsed into this one single point with zero volume.
So it's pretty wacky stuff. So how do we actually get here? So if we think about our star right now just sitting chilling out there in the solar system, it's always got two different forces. You got the pressure outwards that the sun's spitting out due to the chemical reaction of the hydrogen inside. It's a nuclear fusion reaction where the hydrogen turns into helium, lets out shitloads of light, and pushes outwards a certain amount. So that's what's going outwards. And then you've got gravity. So remember, gravity is the thing that pulls everything inside. So it's got these two competing forces, and that's what really makes the size and the volume of the sun now. It's where this kind of settles, where it's equal and opposite reactions, and it just sits where it is now. Now at the end of life, when the nuclear fusion reaction finishes, there's a bit of an explosion. But then after that, gravity is going to try and bring everything back in to where the center of mass actually was. So as it comes in, it gets to the point where there are now two different opposing forces. As things move very, very close together, you got electrons that are moving in random directions and are having a natural kind of push out. And then you've also got gravity, which is trying to bring everything in. But this is also at a much smaller volume than it was originally. So we've got two equal and opposing forces here, one trying to bring everything in and one trying to push everything out. Now, if gravity is at a certain point, which they call the Chandrika limit, then the gravity is going to be greater than the thing pushing it out. So that means it's just going to keep going inwards and kind of flip the equation. So gravity pushing everything inwards and nothing can push it out. And this is how black holes are created. Everything collapses in on itself. And at this point, gravity is greater than everything pushing it out. So nothing here can escape. And that's how a black hole is started.
Far out. Intense.
How do we go there, mate?
Yeah, I think I'd sort of get that, mate. I think the only thing worse than your pronunciation of German names is your pronunciation of Indian names. That was pretty horrendous.
What did I say then?
But I don't even know, but it was not anywhere close. But man, I've got a few questions. I think as I've only grasped probably 40% of it. So there are black holes. Is that true? There are black holes out there. That's
100% true.
Can we see them?
We can't see them because they're black, but we can see the gravitational effect of other stars that are around these black holes.
Okay. And does stuff get sucked into it?
Correct.
So if you're just like flying out there in space, you can't really see it, but you could just get, unfortunately, can just get sucked into it. Is that true or no? I don't know how much is real world stuff versus science fiction stuff.
No, that's absolutely true. You'd know about it though. You'd 100% know. If there was a black hole in our solar system, everything would be revolving around it because the gravitational pull would be so big.
Interesting.
There are thousands of they can be up to much bigger than the size of our sun.
Well, Hawking does say that he said that there's evidence that there is a large black hole at the center of our galaxy, and he says that the size of that black hole is like 100,000 times the size of our sun.
Ooh.
That's a big black hole.
So there you go. So
I don't think you want to get sucked into that.
if you think back to our time analogy, when you're moving into the black hole, because you got almost infinite density, so much mass, you're basically traveling very close to, if not with, the actual speed of light. So when you go into there, the whole idea of time breaks down because you're traveling so fast and time is so slow for you. It gets to the point where 1 second would pass for you, and then the whole universe would end in its existence. It'd be like a billion years would pass for 1 second for you inside that black hole. So it gets kind of wacky. All of a sudden, remember, you got different clocks everywhere. So basically the top of your head would be going at a different time zone to your feet. And this is where it gets wacky, and where Interstellar had the creative license as well to just do whatever the hell they wanted when he just pops in and he pops out and starts pushing books out. Then love conquered all or something. And then
they made a whole new world, didn't they?
I don't know. It kind of breaks down.
It. But yeah, Hawking was saying that, like, imagine if you were like going into the black hole feet first, because your feet, the time that passes, like your head is going to pass a billion years. So you can never actually get in there because for your feet, it's 1 second, but for your head, it's a billion years. So you're already dead before you get in there.
It's an analogy that we got nothing to compare this stuff with. It's everything we know and exist breaks down, and probably falls in that category of science. If you think you understand it, then you probably don't understand it. And if you admit you don't understand it, you probably understand it more than the others. Does that make sense?
It's very confusing, but I think I understand it.
So you don't understand it? Yeah, you don't understand it.
I got no idea.
Next, we're moving into more of a wacky world of quantum mechanics. Have you heard of the uncertainty principle, Ashto? I've read
this book, so yeah. Before that, no.
Yeah. Do you understand this one?
Again, maybe 30%.
So you 70% understand it. Well done.
Yeah, I don't know how that works, but yeah, I do.
Let's call it the atom paradox.
Is this your new law?
If
you don't understand, then you do. If you do, then you don't.
Yeah, absolutely. Let's go with that. So what Heisenberg came up with, not the guy of Breaking Bad, but a much more brutal German scientist. He made experiments trying to determine both the future position and velocity of a particle. In order to measure its location, you need light. And the smaller and smaller wavelength of light you get, the more precise you can get with the location. The smallest possible size is 1 quantum. And as you get to this ultra precision, you can determine its exact location. But the problem is this smallest size of light, the quantum, it actually changes its velocity in a way that can't be predicted at all. In a similar sense, the more accurately you measure the speed of the particle, the less you can understand about its position. So it's a bit of a paradox. You can't measure both the position and the velocity at the same time. The more accurately you try and measure one, the less accurately you can understand the other.
So if I'm understanding this correctly, so something's moving and you want to try and work out, where it is and how fast is it moving. So you need a light to be able to look at it, to be able to see where this thing is. But if you use a strong light with a very short wavelength, you can look at where it is. But the more you look at where it is, that light is actually pushing it in a way that you're changing its velocity. Does that make sense?
I think a hardcore scientist might say it's simplistic for both of us, but I think that's probably a good place to land for both of us.
Yeah. Okay, we'll go with that. Yeah, so if you're using a light to look at something, the light is actually pushing that thing and affecting it in a way that makes it so you can't predict it anymore.
But it's not necessarily like a spotlight. You're just flashing on your head and you can see it. It's more like the very microscopic quantum level. We're using a quantum to observe the effects of the light wave. You're not looking at it, and that quanta is having the impact, and you're probably measuring it, and you're measuring it from indirect means.
So I think what's happening here, what it's boiling down to, is that by actually observing something and trying to understand it, we're actually changing it in a way that we couldn't understand what it was originally. So I think it's saying that, this observation, looking at something, trying to do scientific stuff to understand, actually changes that thing.
Yeah, what it got rid of was the idea of determinism. If you think back to Newton and Galileo with the laws of motion, if you measured everything at the starting conditions of the universe, everything from that point is somewhat deterministic. It would be one hell of a calculation to understand what's going to unfold, but basically everything can be determined and has very little room for any kind of divine intervention or anything like God or anything like that. And that's probably why they were burnt at the stake and all that, because at the time there was no science to remove this determinism. And what this uncertainty principle really shows that there's no way we can predetermine what's going to unfold at the quantum level. Nothing is really deterministic.
Okay, so I kind of understood the Heisenberg uncertainty, the bit about how using a light to look at something to try to measure it actually changes that thing in a way that you can't measure it anymore, or you can either measure speed, or you can either measure velocity or position, but by measuring velocity, you don't know the position. By measuring the position, you don't know the velocity. I was sort of getting that. Mate, this next one is something you're going to have to carry a little bit here, but this is the double slit experiment. And so this experiment, so say you've got a light is shining on a wall, but between the light and the wall, you've got like a bit of a partition with two very narrow slits in it. So you've got a light hits this partition with two very narrow slits and then shines through to the wall. If you think of this as like a particle, so something traveling through, it would act like, say, imagine like a tennis ball. If you're throwing a tennis ball to hit the wall, it would just go through the slit and hit the wall on the other side in that straight line position. That's if it was acting as a particle, yeah?
Yeah, and then depending on what slit you throw in, if you slow it through slit 2, it would just land on the second part of the wall. If you throw it through slit 1, it will only land on the one part of the wall. So it's kind of just two places where it can possibly land, and that's it.
And the same as, even if you threw it 1,000 times, through 1,000 tennis balls, some of them might go through slit 1, some will go through slit 2, but it's really only 50-50, yeah?
The other way it might behave as is, say, a wave. Let's say where the wave at the moment, we're approaching both slits. As the wave goes through one slit, it's basically becoming a new wave. As it goes through the other slit, it's basically another wave. So you've got two different waves passing through these two different splits now, and they're both occupying all the different space as it's approaching the wall. Because you've got two waves, if you think about a surf beach, if you put two waves together, if you go surfing and they double up, you get a really huge wave, and then it can go the other way down and you get a really huge trough. And there's some places where they just cancel out and there's just nothing there. So let's move it back to a light. If you're a light, it's going to superimpose, like you'd have a really huge surf wave, you'd have a really bright light, and that's where they superimpose together. And then you'll have some parts where it completely cancels out. So as you go through the wave, there's going to be the brightest parts, and then as it goes discrete, like you would a wave, next to the very bright part, it's going to cancel out, then it's going to get brighter again, then cancel out. And as you move further and further away, it gets dimmer and dimmer and dimmer. So that's what would happen if it behaved like a wave, if you put light through these double slit experiments.
Okay, so if it was acting like a particle, it's going to go through one of those two slits and it's going to hit in only one of two possible positions at the end. If it was acting like a wave, a lot of the wave hits the first wall, but some of that light gets through each of the slits. It even still continues in that wave style going through, and so when it hits the wall eventually on the other side, you're going to get some areas where the wave has doubled up to make it extra strong. You're going to get some areas where the wave has like doubled up on the negative side, so there's nothing there. And then in between that, you've got sort of a mixture of varying degrees of strength of light hitting the wall.
Well done, Astro. Okay,
it's about to go next level now.
Okay, so next we'll talk about what actually happens. So let's say we put a quantum of light through. It'll hit one location on the wall. So in one sense, it's going through as a particle. But as you do it over 1,000, the pattern it creates isn't the pattern of the baseball hitting single spots. It starts creating the pattern as if it was an actual wave. So it's experiencing interference and cancelling each other out, and got a much larger variety of places that it can land on. So this is what they say when it's experiencing the wave-particle duality of light. It's basically light behaves as both things. There's a very interesting second part to this experiment when it's the act of human observation actually changes how the light actually behaves. You think about that first scenario, the light will go through the two slits and it'll experience interference the whole way through, and then it'll land on the wall in a single point. But when you do it over a large number of thousand, it's clear interference patterns like you would a wave. So here it's behaving like a wave and a particle. So that's all good and well, we've explained that. The second part of the experiment is what happens when you actually observe where is this light quanta before it goes through the two slits. And the single act of observing before the two slits, it actually changes its behavior completely. It turns into a particle mode, and then it only goes through one of the slits and then doesn't experience any interference. So the big difference here is the act of observing before the two slits changes the impact and the result that it has when it goes onto the wall.
Okay, so you've got a person observing after the slits. So they're looking at the wall. The light that comes through, it acts like a wave in that there's light across the whole thing, but stronger in certain points. So there's some strong lines and then a bit of a gap and then a strong line and a bit of a gap.
Yeah, after you've done a huge number of them, it's clear that the results show interference patterns.
Mm-hmm. And then if someone goes to the other side of the wall and they look at the light before it goes through, it just starts acting and hits the same spot every single time like a tennis ball.
That's right, correct.
Yeah, I don't get it. It sounds intense.
It is intense. And that's why there's a lot of spin-offs, your Deepak Chopra style and all that here, showing that the human observation, the human brain warps reality into acting a certain way. And this is kind of what the experiment kind of, in some ways it shows. You could see how they draw a conclusion like that. Whereas I think proper scientists don't probably arrive at the same ideas as your big man Deepak.
You hear a lot of people, whether that's in books or podcasts, a lot of people taking if someone mentions quantum at the quantum level and how business changes at the quantum level, or how you can attract things to yourself through the laws of quantum. Basically, if anyone mentions quantum, who's not like a scientist talking about this sort of stuff, I'm very, very, very skeptical.
Yeah. Well, it's a bit like Interstellar. You got a lot of creative freedom when you get to these points when no one understands, and to a certain point, you could just come up with any narrative to suit what you're really looking to get.
Hawking talks about the universe now, and he says that I guess there's two potential scenarios here. We think that there was a big bang and then the universe started expanding. And from that point, does the universe continue expanding forever? Or does it get to a certain point where it's finished expanding and it starts coming back in, it starts contracting back the other way? And so this is something that Hawking explores here through a couple of chapters of this book, the idea of this universe, I guess the origin of the universe, and then the potential fate of the universe.
In the 1920s, scientists started to measure stars all around the universe. And pretty much if you've got a star, the only thing we can measure really is the light, if you really think about it. We're not close enough to understand anything else. But one thing they noticed about all stars is that they have a shift towards red. They've all got a lot of red in their light, which is an interesting thing. But the way it answers this question that you pose, Ashjo, is we need to really understand the Doppler effect.
Well, if you think of it in terms of like a rainbow, Roy-Gabiv, like so red at the top and you've got your blue, indigo, violet at the bottom. So the red light is the longest wavelength, so the biggest gaps between the peaks of this wave. And the blue at the bottom has the shortest wavelength. And so what we're seeing in these stars is that there's a lot of red, which means the wavelengths of the light emitting them are getting longer and longer and longer.
Let's move away from light for a second and think about a car analogy with sounds. If a car's traveling towards you, it's got a very different pitch sound compared to as it's traveling further away from you. As it's coming toward you, it's got a very high pitch kind of sound, and as it's going away from you, it's got a low pitch sound.
Can you give us an example of how that would sound? Yeah, nice. That was
actually
not too bad,
pretty happy with that. I didn't know what else going to say.
So basically, as it's coming towards you, the pitch is increasing, and so it's getting shorter and shorter and shorter, the distance between you and the car. So the closer it gets to you, the shorter it is and the higher pitched it is. Once it goes past you, the distance between you and the sound starts to get further and further away. And so because those waves are extending out there, the pitch starts to get lower and lower and lower.
Yeah, if you think about it, as it's traveling further away, it sends one sound wave back, and when it arrives back at the car, it's further away. So the wavelength is further.
So how that applies to these stars here is that if something's coming towards you, the wavelengths are going to be getting shorter and shorter and shorter. So the light will be tending towards the blue light, which is the shorter wavelengths. But if things are getting further and further away from you, the wavelengths are going to be getting longer and longer, which means they'll be tending towards the red light. So this idea of this red shift, all these stars shifting towards red light, gives us an indication that things are constantly moving further and further away from us.
So everything's moving further apart. He uses the analogy of a balloon. If you've got a little balloon and you put a lot of polka dots on it and you start blowing it out, as it expands, everything is moving further apart from everything. And this is what we're somewhat experiencing.
So continuing on that balloon analogy, so we're blowing air into it, all the different dots on the balloon that could represent planets or stars, they're all spreading out relative to each other. I guess the question is there a point where it gets too much and the balloon bursts and everything gets ripped apart? Or is there a point where you stop blowing air in and the force going out makes the balloon go back contracted and things start getting closer and closer to each other again?
Yeah, the equation is going to be dependent on two forces. We've got gravity trying to pull everything in, so all the mass of everything in the universe is trying to bring everything back together to the single point. Then we've got the force outwards, which is the initial push of the universe. We don't really know exactly what's going to be the end of it all, but they do, through posing this question, find out about how much gravity is in the universe. And everything we see, including black holes and all the stars and everything, that only accounts for about 10% of the gravity. So there's 90% of stuff out there which we don't know what the hell it is. And then we call it dark matter, almost as if to just act like we know it is, but we really got no idea about 90% of what's out there in the universe and the mass because of it.
Yeah, that's so funny. Mate, one other visual image I liked how you brought this one in because it helped me understand it a bit more, was like if you think of Earth, the planet, and you start at the North Pole, it's got like zero radius. And as you go further and further down, the radius of the sphere increases and increases. When you get to the equator, that's at its absolute maximum there. And then it starts getting less and less and less, all the way down to the South Pole where it's back to zero. So he uses this shape as like potentially like the Big Bang, where there's a size there of zero. It expands, expands, expands. We're currently in this expansionary phase. There could be a point where we get to the equator, which is the maximum circumference, the maximum expansion, and it starts sucking back in closer and closer and closer to zero, which he calls the big crunch. So I guess, mate, they're two pretty bad things. One is it expands forever and rips apart. One is that it crunches back in and all smashes into each other.
Yeah.
Hopefully we're not around when that happens.
I don't think we'll be around, man. I don't think you got anything to worry about. The book does have a philosophical tinge to it. I think Hawking's got a bit of an atheist bias, but he does pose a few locations or areas where God can actually intervene. It's questions like, why was the universe so hot to begin with? Why is the universe so perfectly uniform on a large scale? Why did the universe start with a critical rate of expansion that separates models? Why did the universe start with such a critical rate of expansion? Why is the gravitational constant this certain precise thing? Why is the speed of light so precise? Why is the electromagnetic force, so magnets, why is that so exact? Like, there's at least 100 things in science which are very finely tuned exactly and precisely. And if any of them were 1/1,000,000th of the way out, then nothing would have unfolded like it did for us to be here speaking today on the podcast.
Yeah, I'd say much more than 100 things. There's just all these random things around us in science, in the universe, that seem to be exactly perfect for life to occur on this planet. He used the analogy that if you get a whole bunch of monkeys randomly smashing on typewriters, most of what they put out is not going to work. But every so often, because it's just random, things will randomly work together and they'll pump out a Shakespearean sonnet. And so there's a few different theories to this. Is one theory like, okay, there was just so many different random possibilities and we got the exact perfect one popped out and that's why we're alive? Or maybe there were some really smart monkeys in there.
Yeah, that's right. So the first one's what they call the weak anthropic principle. It's basically that us humans, we shouldn't be very surprised or bewildered or anything. It's, of course, everything was precise because we're here. That kind of makes sense. It's almost too obvious.
It's very weak. Basically, we're here, so everything just worked out perfectly.
Yeah, exactly.
Yeah, that's very weak.
The second approach is the strong anthropic principle. And this is the much more deliberate approach where everything was finely attuned and finely adjusted to make possible the development of life. It's not referring to exactly God or anything. It's kind of got a bit of a tinge to it that it was finely tuned for us to be here. There are very few ranges for intelligent life to develop. There's probably like billions of universes that could exist with no one there to observe its beauty for everyone that can be there to observe it. It's pretty incalculable, the odds of everything coming together for us to be here. What do you sit on, Ashjo?
Mate, the more I think about it and listen to other people talk, maybe it's just all a simulation. maybe they're both wrong, and we're just
not scenario one, not scenario two.
It could be the third, which is we're just living in a simulation.
Well, it's a pretty deep rabbit hole. Whatever you go down like this, then you'd say, all right, whoever's in the real world doing the simulation, what was it for them?
Well, that's the thing is if we get to the point where our intelligence is so great that we can create artificial intelligence, we can create games or programs that can replicate the real world, then what's to say that we aren't in that ourselves? And so, yeah, it could be infinitely many layers back to get to the original person who coded that.
But then the original
simulation.
person, is it the weak anthropic or the strong anthropic? That's my question, Astro. It's turtles upon turtles upon turtles, your argument.
All the way down.
Turtles all the way down. So it's a good book. I hope no one was driving whilst listening to this episode, because you probably would have crashed by now. You would have crashed because there's a lot of system 2 in listening to this content and also reading it and also doing the podcast. My brain's absolutely cooked. But I think it's a phenomenal book to access some of the really interesting and exciting things about the universe. If you're that way inclined and interested in things, then this is a great book. If you've been listening for a while, I think you'll know by now that me and Astro, we both love a good read, and the ones we love the most, we've really put down, ranked and ordered into our top 50. We juked it out because some books we agree on, a lot of them we don't agree on, but I think this top 50 we both agree is pretty freaking phenomenal. So if you want to check it out, head to whatyouwilllearn.com/top 50 and you'll be able to get it for free.